Welcome to part 3 then, assessment for general characteristics. Now, what do we mean by that? General characteristics, when we're designing our system, we need to know what's involved, what kind of supplies it's going to need, what kind of equipment's going to be required, where it's going to be installed, and we need to make an assessment of what our customer wants and how we are able to provide that in the safest manner. So through chapters 30 to 36, we will assess things from the general characteristics, the purpose, the supplies and the structure, the classification of external influences. We need to look at compatibility, maintainability, any safety services that may be involved, and we need to look at designing a system that's fit for continued service. Each of the chapters will cover that individually. So Chapter 30, 301.1 says an assessment needs to be made of all the following characteristics of the installation in accordance with the chapters. And it refers to the chapters we just covered, 31 to 36 there, and the purpose of the installation, general structures, the external influences, compatibility, maintainability. All of these things need to be built into our... So, chapter 31 then, 311, maximum demand and diversity. We have to design our system to be reliable and economical in running. So it's got to be installed within thermal limits and admissible voltage drops. We've got to select the correct cables and maximum demand needs to be determined. If we don't know the maximum demand, we can't inform our suppliers as to how big a supply we may require. So determining maximum demand involves looking at diversity as well and of course potential power factor issues within the system. Power factor, of course, being the reactive power, the froth on the top of the beer, the bit of the electricity we pay for but we don't actually use. Chapter 31 then, for maximum demand, we need to take into account the following. We need to look at time profiles, coincidence of electrical loads, mechanical loading of electric motors, seasonal changing. We turn the lights on in winter, we turn the heating on. We turn them on a lot later in summer. Any special requirements for a particular installation, multiple shower cubicles, changing rooms, maximum demand and diversity. And then of course, maximum demand is determined by connected load multiplied by the diversity factor. We need to look at earthing arrangements. We've got one or two diagrams here and they'll be in the book on chapter 31, section 312. We've got single phase, multiple phase. You may well get a question in the exam asking you to identify one of these. It may be just a simple phase angle of 120 degrees two-phase system, or it may be a three-phase system. Have a look at these pictures in the book. And of course we've got our four main earthing systems, TNS, TNCS, TT and IT. IT is covered by Appendix 9 and it's not something we'll be going into in any great depth during the course of this course. So what do those letters refer to? T, terra, the earth, N, the neutral, C is combined and S is separate. And those are the earthing arrangements which we'll now look at a little bit closer. Typically when you look in a household or a standard single phase distribution, this is the kind of scenario you'll see with the little earthing points there. On the left we've got a TNS system, TNCS where it comes out of the side of the head, and a TT where it goes down to an earth rod. Now here's a bit clearer diagram of how that's wired. Here's a TNS system where neutral and earth are run separately, whereas with a TNCS system, earth and neutral are combined at the source and there may be additional source earths throughout the distribution, and it's separated back out to earth actually at the consumer end. Or alternatively, we've got the TT system where no earth is actually provided by the supplier, but the earth rod's installed by the installation electrician who's built the system, and the earth electrode picks up the earth potential local to the installation. Now, other things we need to take into account at this point is the characteristics of the supply or supplies, from what source they're coming from, the voltage range, nature of the current and frequency, prospective short circuit at the origin of the installation, the ZE, earth fault loop impedance of the system, suitability of requirements of the installation for maximum demand, and the type and rating of the overcurrent protective devices at the origin of the installation. All that kind of information should be provided by the distributor on request. Now, any safety services 313.2 that we may be required to install will have to be assessed, and such supplies need to have adequate capacity, reliability and rating, and appropriate changeover times for the operation specified. For standby systems, that there's no particular requirements in these regulations. They tend to be in a separate guidance themselves. They'll come under a different British standard. But 314, every installation shall be divided into individual circuits as necessary. Now, this is not only a recommendation or regulation in the book, it's very, very good practice, because it avoids the danger of inconvenience if a system fault arises. If, for instance, an entire house was on one fuse, if the fuse blows, the lights go out, the sockets go dead. Until you find the fault, the whole house is off. If we divide it into separate circuits, upstairs lights, downstairs lights, upstairs sockets, there's always a provision of some form of electricity. It's good practice on the modern split RCD boards to put upstairs lights on the same RCD as downstairs sockets, and vice versa, so that we've got a source of light either by plugging in a table lamp or turning on the light on each floor at all times. And the other advantages with splitting into multiple circuits is, of course, it reduces the possibility of unwanted tripping of the RCDs due to excessive protective current in the protective conductors. And we can also prevent indirect energizing of a circuit that's intended to be isolated. 314.2 says that separate circuits need to be provided for parts of installation which need to be separately controlled in such a way that those circuits aren't affected by the failure of another circuit. And the number of final circuits, 314.3, and the number of points supplied by any final circuit shall be such to facilitate compliance with the requirements of Chapter 43, which we'll cover later for overcurrent protection, and Chapter 52, isolation and switching. And where an installation comprises of more than one final circuit, each final circuit shall be connected to a separate way in the distribution board. The wiring of each final circuit shall be electrically separate from that of every other final circuit, so as to prevent indirect energization. External influences, which is actually has its own appendix, Appendix 5, and is covered again in Chapter 51, needs to be taken into account when we're designing our system. We wouldn't want to put a system in that is going to be subject to a major external influence, such as direct sunlight or water, or the potential. We've got there in the pictures there ivy growing on the outside of a house. If we were installing cables external to that property, we would need to be looking at protecting it on against flora and fauna. As I say, we will cover that further when we get to it. Now, when we get onto compatibility, Chapter 33, we need to look at things like transient voltage, under voltage, unbalanced loads, fluctuating loads, starting currents and harmonics, DC feedback, high frequency oscillations, and the all important power factor. All our systems need to be compatible and need to be able to work together and work without interfering with any other systems. Electromagnetic compatibility consideration needs to be given to the design for installations of ways of reducing electromagnetic interference to other systems, and we need to comply with any relevant EMC standards. Now, Chapter 34 is maintainability. Every system needs to be assessed to assess the frequency and quality of maintenance that can be reasonably expected to receive during its life. Anybody designing the system needs to design in things like access for it and ease of maintenance. And the designer needs to start looking at periods for a different distance between inspections and testing. Maintenance is likely to be necessary during the intended life of the piece of equipment, and the effectiveness of the protective measures for safety during the intended life, making sure that they don't diminish. The equipment needs to function properly for its entire intended working life, and there may be particular statutory requirements relating to how often maintenance frequencies need to be set. So when designing the system, we must design in a maintenance plan for the system's entire life. Safety services, of course, can be things like backup generators, storage batteries, primary cells, generator sets, even a separate feed. And the need for safety services and the nature and the frequency that they need to be maintained is also sometimes laid down by statutory authorities. Typical safety services are emergency escape route lighting, fire detection, fire alarm systems, installations of fire pumps, fire rescue service lifts, and smoke and heat extraction equipment. All of these safety services need to be built into our system design, and any particular requirements need to be covered. And then finally, Chapter 36. Once we've designed our system, it needs to be fit to continue service without being looked after too much. We need to plan our maintenance, as we mentioned previously. An assessment needs to be made for each circuit for the need for its continuity of service, and an assessment of its intended lifespan, of course, as well, and any necessary backups that need to be put into place for it, such as multiple power supplies or monitoring devices. So as you see, part 3 is an assessment. It's having a good look at what we're expected to produce. What are we going to design our system? How big the demand is, what kind of supply voltages and things we need, what kind of protection, not just for overcurrent, but what other protection services do we need? Protection against fire, protection against external influences. All of these factors need to be built into our initial assessment and planning before we can get into the actual design and creation of our system. All of that needs logging, and it needs looking at from the point of view of maintainability and future proofing. And that's our assessment for general characteristics section covered then. I'll be back with part 4, but in the meantime, thanks for listening.